Welcome to the next lecture series of the ongoing course Perception Algorithms for Autonomous Systems. We are studying in last class we have completed measurement system modeling. Primarily we have completed a pulse Doppler radar, phased array radar, electro-optic and infrared sensor, how the measurement models are behaved. We also solved from the pseudo measurement conversion approach from when we are tracking if using a linear Kalman filter. So, that means my measurement is in a cylindrical or polar domain and I am converting it into the Cartesian domain. How the measurements as well as its associated covariance is converted in each and every dt, we discussed the equations of that, and also we have found out that my R matrix is kind of a correlated. Okay. With this now I have started last class only the false alarm simulation. As I told, false alarm means fictitious target. There is no target, but you still are getting some measurements. So, this is called false alarm. So, in this false alarm now I will simulate it. We discussed enough false alarm in my last class. So, this class we will be kind of telling how to simulate it for your when you simulate your total measurement set along with your valid target. Okay. So, first is that what is the normally false alarm can be simulated in multiple ways. The popular most approach is to simulate it from a Poisson distribution. What is a Poisson distribution? Again, I will explain it in my subsequent slide. So, from a Poisson distribution. So, how to simulate it? So, expected number of false alarm, say I am denoting it say NFA, is actually false alarm probability per scan cell volume, that is PFA, into the total surveillance area volume. So, what is all this thing, what does this mean? What is mu FOB? Mu FOB is actually, suppose your radar is surveilling certain area. Okay. If it is a 2D radar, if it is a 2D area, if you can say only XY this thing, then it will be an area. But if it is a 3D environment, it is actually tracking, then it will be a volume. Okay. So, what is your, so this entire thing is your FOB volume. So, your x, there is a x mean, there is a x max, there is a y mean, there is a y max, there is a z mean, there is a z max. So, with all this thing, now you can calculate the volume of this cube. Okay. So, that you have calculated here. So, volume of your FOV, that will be volume of your FOV. So, what is PFA? PFA, as I said, that false alarm probability per scan per cell of volume. So, this is actually how much approximate number of false alarm that can be present in the thing, that is the designers kind of can give you this information, the sensor manufacturer can give you this information. So, with this the average number of false measurement in each and every scan, and remember this number of false alarm will vary each and every scan. If scan 1 there is 5, scan 2 there could be 10, scan 3 there could be again 2, there could be things. So, this is entire a random number. Only thing I am doing, the false alarm frequency, the number, I am modeling it as a Poisson distribution. So, mean number of false alarm first I will calculate using the above equation, false alarm probability into your again I have done it using in a cylindrical way, but you can do it in a XYZ also, everything is valid. So, actually your max range minus mean range divided by range error, max azimuth minus mean azimuth divided by azimuth error, elevation minus divided by elevation error. Okay. So, this will give you, this equation will give you what is the mean number of false alarm. Now, you simulate a Poisson distribution. So, Poisson distribution is again kind of a Gaussian, it is a Gaussian distribution, not a kind, it is a Gaussian distribution only, whose mean and covariance has some relation. Now, in Gaussian distribution, you know there could be a mu p, mu is actually your mean, and there is a p, the p is called variance. Now, in a Poisson distribution, your p would be a square root of mu, square root of mean, your error variance. So, that is actually a Poisson. So, if you can see your Poisson distribution is like this. So, if you just simple, and it will be actually an integral multiple. So, if you since because I am simulating the number, so I am taking the absolute value. So, absolute with the rounding about mean FA plus square root. So, this is mean plus square root of this thing into Gaussian this thing, Gaussian number of 0 mean unity variance. I got the number of false alarms. Okay. Once I got the number of false alarms, I can now simulate my what is my false alarm range, azimuth and elevation for all the false alarms, the numbers that I have selected for that particular scan from a uniform distribution. Uniform distribution is what? Because your x max, x mean, r max, r mean, or whatever you say, y max, y mean, z max, z mean, it is all from uniform, because from anywhere the radar is surveilling, from anywhere it can pick a false alarm. So, it should be simulated from a uniform distribution. So, uniform distribution is how to simulate uniformly distributed random number, mean plus max minus mean into uniform number, 0 mean unity variance. Same thing I have done here. So, I simulated for range, I simulated for azimuth, I simulated for elevation. Okay. So, n is your Gaussian distribution with 0 mean, and this is your variance. With this I have done. So, this is actually my stochastic false alarm situation. Each and every cycle this is vary, because each and every cycle I have to simulate number of false alarm, and each and every cycle I have to simulate for those number of false alarm what are your values of your range, azimuth, elevation, or x, y, z, what if you do in this Cartesian form. Okay. And this will be appended with your, or this list will be included with your target oriented measurement. So, your radar is giving multiple list. Now, you do not know which is from target, which measurement is from false alarm. You have to solve that. That is the idea of tracking, multi-target tracking. We will talk later. With this, I would like to complete the measurement simulation, model simulation part. So, you have seen MMSE estimation, you have seen maximum likelihood, we have seen map. We have given you some basic things. You have detailed, you have studied least square method. Okay. Lavenbar-Marquardt I have not told, RLS also I just omitted, but at least some first order fit, second order fit, since it is directly implication to tracking, we have covered. Maybe in estimation theory course you will learn this thing a lot. Kalman filter we have covered. Okay. Okay. There are something called as particle filters, sequential Monte Carlo technique, we won't talk. We won't talk here. Now, Kalman filter, we talk about linear filter. We have discussed a lot, because this is the heart of tracking. Kalman filter and least square are the heart of tracking. So, we discussed about it. These two also we have not talked. Information filter, square root filter we have not talked. Information filter may be something we will talk in the future. Square root filter also in different fusion, if we talk, we will have a very bare minimum kind of this thing. We will be talking this thing, extended Kalman filter. You have to talk, because this is, because your radar measurements, UIR measurements are non-linear. So, I have to talk this. We will talk about pseudo linear filter. These two we will talk. Sigma point filter, I will give you just bare minimum information, so that at least you know what is sigma point filter. These things we won't talk. And up to EQF only, we will talk only first order EQF. When we solve some problems, we will show basically between this and this how the methods actually are working. Now, coming back to the extended Kalman filter. What is called an extended? Kalman filter, you know, Kalman filter is an observer that estimates the states of your system. The system dynamics is also corrupted with white Gaussian noise using some measurements. That measurement system is also corrupted with white 0 mean white Gaussian noise, and it tries to estimate the system. Fine. Whatever in control system terminology, whatever is the Leuenberger observer, it does same thing in the stochastic observer or optimal observer. Okay. That is all Kalman filter is. Kalman filter operates in linear system, does not operate in non-linear system. That means A matrix and H matrix has to be linear. Extended Kalman filter, what it does? It is just simple. So, your xk equal to phi of xk minus 1 plus of wk, y of h of xk, or h of xk plus your vk. Okay. So, these two has to be linear. Now, in a non-linear system, what you will see? Suppose you are using nearly constant turn rate model. You remember when we studied this thing, your state matrix is a non-linear because of inclusion of your omega, and your y, say you are using now tracking it using a radar. Obviously, it will be a non-linear system. Okay. So, this is now, sorry, this is I am telling it say G, not same F. So, say this is I am telling at G. So, this is a non-linear function, this is a non-linear function. Okay. Now, I have you know now only your one method to solve it. If it is possible, you convert it to measurement to linear, and then you estimate your this R matrix accordingly. But if it is you want to solve using a EKF, EKF does not do all this thing. It will do simply first order Taylor series approximation of your state of your measurement. So, that is all it is doing here. So, it will do the first order Taylor series linearization about the mean of the Gaussian random variable, right. I have done simple Taylor series here. So, only thing, just do not get confused. I have noted this measurement as y, here y, but here just a function I have written as y. It is not measurement, do not get confused. It is, so maybe I can term it as z, that will be better, just a ease of confusion. Okay. So, y equal to say nonlinear function plus w. Now, x means x bar plus delta x is the perturbation. Okay. Any kind of small perturbation theory and all we know. So, with this plus w, you do a Taylor series linearization, first order, and you take, suppose this is the first order term, this is the second order term plus higher order term plus white noise, process noise. Okay. So, now I cut this because I want to do only first order. So, I am having only this. Now, you calculate mean, you get it, expectation of A plus B plus C is equal to expectation of A plus expectation of B plus expectation of C, 0. Expectation f x bar constant. So, that term is coming here into delta f is the Jacobian part, delta f means is the Jacobian into E delta x. This is also assuming a Gaussian noise, or 0 mean wide Gaussian noise, it is also coming as 0. Okay. And you can calculate your variance. So, variance, if you calculate it, expectation of y minus this thing. So, mean minus mean bar, or your the average, mean minus actual variable minus average bar, you get it like this. If you solve, it will be like this. So, this is also similar in A P A transpose plus Q, that is what your linear Kalman filter predicted error state error covariance equation looks like. So, here it is like this. Okay. So, this is called variance. Now, again the same table, same Kalman filter table, only thing there is no change, only thing I am doing some linearization for my state transition matrix to get, and for my measurement matrix, observation matrix. Now, very important one thing which should you keep always in your ear, extended Kalman filter linearization of the state transition matrix is required only for covariance calculation, not for the state calculation. So, state, you use your simple non-numerical integration method like your Euler integration method or your Runge-Kutta second order or fourth order, whichever you wish, you can use it. But state won't be approximated, state estimation won't be approximated using your linearized matrix. So, here prediction when I am doing, I am using simple Euler, Euler is okay. You want to use Runge-Kutta, no problem. Okay. So, Euler integration only I am calculating my predicted state. So, predicted state is equal to my posterior, predicted state at t equal to k is equal to my posterior state or estimated state at k minus 1 plus your nonlinear function computed at k minus 1 into sample time. Okay. Simple Euler. Next, for this phi matrix computation, I did a Jacobian of my nonlinear function based on my posterior value at k minus 1. Estimated value and posterior value both are same. So, estimated is called posterior, a prior is called predicted value. We can use this terminology also in the lecture. So, with this I have calculated my phi value. So, this is my actually A. So, phi p price number plus same Kalman filter equations. So, with the predicted state and predicted error covariance, you go to the estimation cycle. Once you go to the estimation cycle, you calculate your innovation, predicted measurement, actual measurement minus predicted measurement. So, your prediction and actual measurement, what is the discrepancy is there, that is called your innovation. Now, you have to calculate Kalman gain. Again, in the posterior cycle, we will use the same term, but for the Kalman gain computation, I have to use linearization of my H matrix. So, here you see I have done linearization of my H matrix. So, and here I have used my predicted state or a prior state. So, my predicted state x k minus 1, I have used my predicted state to calculate my observation matrix. Okay. With this observation matrix now, I got my innovation error variance, and then now this is output covariance. So, output covariance into innovation covariance inverse is what will give you the Kalman gain. So, I have added this correction Kalman gain into Z. So, rest are all Kalman filter equation. So, estimated state is at t equal to k is equal to predicted state at t equal to k plus your Kalman gain into residual, the correction part. and your estimation error covariance, again I have to use the k. So, I minus k into h into pkk minus 1. So, this h value is used only for Kalman gain calculation and for pkk calculation. Here I have not, you should remember, here actually I have not used in a kind of anyway this linearization or so. Okay. So, even predicted state calculation also I have not kind of used it, okay, because when I am calculating residual, you see I have put it using nonlinear function h of x k k minus 1. I have not used it h of x of k k minus 1. I have not used it. I have not used it. So, this is the thing. I have not used the linearized value in computation my predicted measurement. I have used the nonlinear function only, because if I use the linear value, my innovation will be of erroneous and that will impact my estimation. Same thing is here. If I use suppose a into x k minus 1 k minus 1, if I use say a into x k minus 1 k minus 1, so that means what it will happen? It will have a negative impact in your estimation. So, we won't use it. We will use simple numerical integration. So, this thing only if you need to keep in mind, rest are all Kalman filter. So, this is all about your extended Kalman filter. Okay. Now, we will solve a problem. So, with EKF now I would like to kind of tell one example. So, suppose I want to estimate a sinusoidal signal with unknown frequency estimation. Okay. So, suppose you have a signal, suppose you have a sensor, that sensor is giving you some kind of a sine wave, but you do not know the cycle, the frequency, the cycle you do not know. So, x equal to a sin omega t. Okay. At least you know the signal, the measurements which are coming from your sensor may hold a sinusoidal. If you do not know, then how will you model it? Then you have to model it like this, x dot equal to white noise. So, you remember when I was teaching the target state matrix modeling. So, that time also I told whenever the things are not modeled properly, your knowledge is not there, a simple unknown, you can take x k equal to x k minus 1. So, that means it is a Wiener process, or even we should do it as a first order Markov also. So, x dot equal to minus alpha into x plus white noise, when you have no information of the signal how it is looking like. Here I know my data points may reflect a sinusoidal signal, my measurement points are whichever coming from sensor sinusoidal thing, but I do not know the frequency, frequency is unknown to me. So, I can enforce this knowledge in my modeling. So, this example is a good example, at least it will show you how to model when the things are unknown. Suppose you have a data set of measurements, when you have no information of this measurement, you can model it, the two sampling instant, it could be a white noise, the difference is a white noise. Okay. In deterministic, you model it x dot equal to 0, that means 2 sampling instant it is constant, okay. But now you have modeled it as a white noise. Okay. Now, with this I am bit fortunate that I know my signal could be a sinusoidal. So, I will use this information, this is very good information. With this my estimation will be more and more better when I use the KF or whatever I use. Okay. So, if you model it this way and try estimate, you can see this estimation will be better than this estimation. You can yourself see. We will solve some assignment, there you will see. So, x double dot equal to minus a omega square sin omega t, just I am doing some derivative and all. So, you can see this x double dot equal to minus of omega square x, you can yourself model it. Okay. And omega fellow is unknown, omega could be anything. Here I have modeled it as a white noise. So, you got x, position, velocity and omega, all these three states together I got this kind, this is a nonlinear equation, because this is a function of omega, this is a function of omega, function of your state, your A matrix. So, it is a nonlinear system. Okay. Now, I would like to, and your what is your measurement now? Measurement say is your x data point. So, x m equal to x m plus this thing. So, maybe I can write it here. So, your measurements is equal to x m is equal to x m plus v. This is your measurement, this is your state. So, you have everything. Now, you will run your Kalman filter or EKF as so called. EKF means you have to do some linearization. So, first calculate your Jacobian of your nonlinear this matrix. So, you get it like this. Okay. Now, there are two ways to do EKF. One is called linearized discretization, another is called discretized linearization. Big name, but the method is very simple. Linearized discretization means first you linearize, then you discretize, also okay, or first you discretize, then you linearize, that also okay. So, here I have done it first linearize and then discretize, this approach. You can do vice versa also, no problem. So, first I linearize it, I got my linear system like this, and then I do my e to the power at, that I plus at. I got it like this, okay. It's like this. So, this is my phi matrix. When I replace my small t with some sample interval, I got like this, okay. I calculated my Q matrix also. So, if you solve the integration and all, you can get my Q matrix also. But this will be a part of your assignments and all. You yourself will see, because I will give you some hints and you will solve the problem, that will clear the things. So, you get now your phi state transition matrix, you go get your Q matrix, and this is your measurement, okay. So, your x is your measurement. So, I have written it into Hx format, H is your 1 0 0 x plus noise. So, this is going to be your state equations. So, your state will be say this one, first row of your Kalman gain into residual, second row and third row. So, this is actually will be 2, this actually will be 3, okay, with this. And with this now actually you have this is actually will be 1 only, I am sorry, this will be actually 1, because this is one measurement. So, only one this thing will come, okay. So, this thing will be same only. So, you get now your true versus estimate. You see now it is kind of a pattern, at least it is holding the pattern. Although tracking I won't say it is very good, but at least it is holding pattern. This is your estimated, this chain dotted line is your actually true, and this is your actually your frequency, this thing, okay, frequency, the constant frequency whichever you are having. So, that is your actually Z. So, but you can still better it. How you can better it? Because in this simulation I have taken my Q equal to 0. That means, I have assumed that I am so confident that I have not taken any Q. Even I have taken my phi s also 0. My this frequency of my knowledge of this thing, I have assumed that my omega dot is equal to not white noise, it is actually 0. So, omega k equal to omega k minus 1. This is the problem that I have made. This is the problem I have made. So, if I now you give a small q and resimulate it, I will get, this is a representative plot again, I will get like this. I will get a perfect sine wave. I will get a perfect sine wave, and if you see the error of your position error, it will be go to 0. Okay. So, this is actually a representative plot. This is actually a representative plot to show that how the in extended Kalman filter things are kind of changing. We will solve this thing as per in a assignment. The same problem we will solve, so that at least things will be clear to you. So, just let me do the summary. So, we learned EKF. What is EKF? EKF is a first order Taylor series linearization of the mean of Gaussian random variable. So, my state matrix is nonlinear, my measurement matrix is also nonlinear. When this is the case, I want to use linear Kalman filter, I linearize my nonlinear state equation using first order Jacobian, and second order and you can use second order state this thing also, but normally it is not very popular. Normally first order approximation or the Jacobian calculation is popular, Hessian calculation or second order approximation is not so popular, but there are literature papers people have done for second order EKF also. It is better, but does not give a big difference and all. So, you start with your initial state is your actually Kalman filter initialization, same as Kalman filter, system dynamics equation, measurement equation, this all are fine. So, here we talk only first order because we have not done second order. Okay. So, first order only EKF we have studied. So, with the first order EKF, so you have now two cycle, one is your prediction cycle, one is your measurement cycle or estimation cycle. In a prediction cycle, first you use nonlinear integration or any integration method, numerical integration method to calculate your state. If you remember this thing, so state you calculate using any Euler or any Runge-Kutta second order or fourth order, you integrate your state, get your discrete state, then you linearize your F matrix using del F by del x, you get your coefficient your state transition matrix linearized. With this you calculate your state error covariance phi. Phi will be actually del f by del x at posterior value or the estimated value at t equal to k minus 1. With this now you calculate your state error variance at predicted level. So, phi p phi transpose plus q. So, predicted state error was calculated. Now, you go to your estimation cycle or posterior cycle. So, here first you calculate your measurement residual. Residual is your actual measurement minus predicted measurements. Do not use h dot h into x dot, you should use h is a function of x dot, use the nonlinear function to calculate your residual, because if you do linearized function then it will have a error. So, calculate residual, then you calculate your Kalman gain, all are same. Kalman gain is you again output covariance into innovation covariance inverse. When you are calculating your innovation covariance, you need the value of h, linearized value. Again using your predicted state, you linearize your del h by del x into your compute at your predicted state, you will get the h value. With the h value, now you calculate your innovation error covariance and output error covariance, you get the Kalman gain, output error covariance into innovation error covariance inverse, you get the output gain. Once you get the output gain, you calculate Kalman gain into residual, that is your correction. That amount of correction is need to be added your predicted state. You get your estimated state at t equal to k, and your I minus kc, k into h into predicted state error covariance will give you your estimated state error covariance. Okay. So, all this thing is actually written here, okay, in words. What I just told in as per in summary and all, everything is written here. So, you have only Jacobian calculation and all. Okay. So, this is all about the extended Kalman filter. We have solved a problem also today with sinusoidal signal estimation, how the things are behaving, that we checked it here only. In the next class, what we will be doing, we will be solving the pseudo measurement filter, how the pseudo measurement filter is looking like, and one particular very important interesting problem we will solve. That problem we will solve using EKF plus the pseudo measurement filter, perfect tracking problem, and we will show you how EKF fails, and that will at least tell you that where are the problems with EKF with this first order algebraic linearization, because these are all algebra, because you are calculating approximating the mean of the Gaussian random variable, because just you are approximating it using the mean. If you go through the EKF equation, you see this, you are approximating using only the mean value, but you are not considering the probabilistic spread. That itself is a wrong approximation. Okay. So, that example will tell you how to kind of run an EKF and a pseudo measurement filter and which one is better. Okay. With this kind of a talk, I would like to conclude today's lecture. So, thank you for your time. So, let us meet for the next class. Thank you for your time.